So we've said we want to find this position of the equivalent particle. Well, how are we going to do that? We need that to be such that the particle has the same momentum. We've already established that the particle has the same mass. So let's sort of think about what this fictional particle must be like. Well, one of the things this fictional particle must be like is it must have a mass big M that's equal to what the sum of all of the masses that make up this other object are. So I'll say it's the sum from I equals 1 to n, right? However many particles make up this extended body. The effective mass, the equivalent mass of the point mass, is just the mass of all the stuff in there, right? If it has the same momentum, then that momentum must be big M times drcom by dt, right? So the momentum is the mass times the velocity, but the momentum also must be the summation of all of the momenta of the individual particles in the system, right? So the mass of the ith particle times the time derivative of the position of the ith particle, or the mass times the velocity of the ith particle. Okay? So now we've got this fictional particle. We know that the momentum has to be this. We know what the equivalent mass is. Can we use those two things to figure out where the equivalent particle is located? Well, it's certainly possible to do that if we manipulate this a little bit. One of the ways that we can manipulate it is look at this and say, well, m sub I doesn't depend on time, so I can take this time derivative and bring it outside of the summation. So I get d by dt of the summation of m sub I times r sub I. And then I can start to see that, I've got big M times drcom by dt is equal to d by dt of the summation of m sub I times r sub I. So the total mass times the time derivative of the center mass position is the time derivative of all of the individual momenta, which finally allows me to divide through by big M and take out the time derivative, at which point I get the position of the center mass is equal to a summation of m sub I, r sub I, divided by big M. So that's just math. Let's take a second to think about what it means. The position of the center mass is, first of all, from a units perspective, you can see you've got mass times position divided by mass, so the units work out, okay? The second thing you can see is that that position is obtained by taking each position of an object inside of this system and sort of weighting that position by how much mass there is. So if I imagine having some system that has a little mass here and a little mass here and a great big mass over here, and I wanted to find the center mass of that system, well, in order to do so, I would basically say, okay, here's, let's say this has a mass of 1, this has a mass of 10, this has a mass of 1, right? There's R1, there's R2, and there's R3, right? If I wanted to find the center mass for this, I would say, okay, well, that's got to be 1 times R1, so 1 kilogram, presumably, plus 10 times R2, plus 1 times R3, all divided by the total mass. Well, the total mass is 12 here. And as you can see, I'm going to be heavily weighted towards R2. In other words, my center mass position is probably going to be someplace pretty close to the center of this guy, right? So this is about where my center mass location is. Okay? So it sort of makes physical sense. It's actually sort of the average location of the mass inside of this object. So when you go from an extended body to a point mass, what you're actually doing is abstracting that extended body and saying the only thing I actually care about is the total momentum of the system. And the way that I can figure out what that total momentum is by asking the question either how is each individual particle moving in the system, or by asking the question how is this effective particle, this equivalent particle, this fictional particle that's located at the center of mass moving. So That's sort of the idea of center of mass. It ends up being an incredibly useful idea because now, instead of trying to figure out what the dynamics are of its whole complicated system, we're instead dealing with the dynamics of a single system. And so we can start to say things like, okay, what's the equation of motion here? Well, the equation of motion for this is simply going to be the sum of forces on the object tells me what the time rate of change of the momentum of the system is, right? So sum of forces on the system tells me the time rate of change of the momentum of the system, which is simply d by dt of the total mass of the system times the velocity of the center of mass. Okay. So even though you've got some extended system that has a lot of forces acting on it, and the forces might be acting on different particles, the system as a whole is going to move in the way that the center of mass moves.